Okay, let's get started. So in this video, we will be talking about linear function approximation. So if we talk about linear function approximation, what is it actually that we are doing? So what we are actually aiming for is we want to approximate a value function or a state action value function with some function approximator that is defined through a set of parameters w. And if we do linear value function approximation, we just derive, what we usually do is we derive a set of features over our state S and find a parameter vector w that through a linear combination of that actually approximates the value function. So what we usually know is like having something like a house price prediction problem where you can do a linear regression problem where you just multiply the point in here and defined by the size and the price, and you just find a set of parameters that actually approximates well this function. And there is a lot of different basis function that actually defines our features well, so that we can actually find parameters w in order to approximate the underlying data very well. One thing to mention at this point is why we do linear function approximation in general. This is meaning that the features are linearly combined, so linear in their weights, but the features itself they might also be non-linear. So actually, what you do in order to derive the feature from the input state is actually up to you, and this might also involve a non-linear operation, which is then combined with a linear combination of weights, meaning that there's actually more possibilities than you would actually expect from that. And why we also want to use linear function approximation is because that you will see in the end, for linear function approximation, we can derive convergence guarantees and we can also, which is something that does no longer hold for nonlinear function approximators, which are very hard to actually train and stabilize in training. We will see this in the next video. And another thing is that linear function approximation is very efficiently to compute, and they are not really data hungry. So this is the second the advantage of these. Okay, but in the end, this largely depends actually on how we represent our states and the features, as this actually introduces prior knowledge. So, okay, if we're talking about how can we represent our state space through a set of features, there's a lot of prominent features that have been successfully used in the past, and I will actually explain a few of them in the upcoming slides. So one of the example features is actually to build a permutation on polynomials over the available input dimensions. So what you see here is what you could do is you could transform your input space, so actually the features that you're defining, as different combination of polynomials over the available input dimensions. Let's do an example from this. So imagine that actually your state is two-dimensional. What you could then come up with is you could in this case, so k is actually the number of elements in your state, and what you define is you wanna actually use n-order polynomials, which actually leads to n+1 to the power of k different features. This is actually what you build up with this, and an example of that is given here. So in this case, k is 2, so actually our input state is two-dimensional, and we want to do an n-dimensional. We want to derive an n-dimensional polynomial basis on the input state. So in this case, n equals 1 or n equals 1, and what you actually want to derive from this is a combination of the different input dimensions through building up the polynomials. So actually, in this case, you could say I will derive from state dimension 1 and state dimension 2 a polynomial basis that is actually containing 4 different elements, which is a1, which is just a linear thing, and s1, s2, and s1 times s2. And you can actually come up with very much more complicated combinations of that. So if you do n plus, so actually if you make if you actually set n equal to 2, you derive n plus 1 to the power of k, so it's actually n plus 1, 9 different state dimensions from a two-dimensional input space, and in this case it simply builds up to 1 as 1 as 2, and the combination of all the different powers of the input states multiplied with each other. And what you actually see is that deriving such a polynomial basis actually lets you derive, like if this is your input space and you transform your state space using this polynomial basis, you can actually find a set of linear parameters to actually describe this polynomial regression function in here. And this is actually the general idea behind your basis function. With more complicated and also maybe nonlinear basis functions, you can find a set of linear parameters and optimize these linear parameters to fit your data well. This is one thing. You can actually choose a polynomial basis to actually derive your state. What you actually could also do is known very well from image processing, or actually in general signal processing, is to use the Fourier basis. So in this case, you would actually derive certain basis function over your input data, and you would find a set of frequencies that actually describe your data well. So in this case, the Fourier basis for I until n, what you actually see here is you see basis functions for different I. Actually, this one in here, which is actually making your basis function, adding a higher frequency to your basis function, because actually the phases changes much more. And if you actually see zero would actually be a constant function, and you can actually use a set of basis functions actually with different frequencies to actually describe your data as a combinations of them, which is actually also very often used in image processing, where you in the JPEG standard, you for instance use a discrete cosine transform, where you also there's a two-dimensional problem which makes it a little bit more complicated in the visualization, but it's working quite the same in the same way, where you actually describe your image through a set of frequencies and how actually the values within a certain range, how they are actually evolving. Yes, and then you can also, you can actually describe also in an image you can describe very well nonlinear transformation through a set of parameters that actually describe how your image evolves. Also very often used in practice in reinforcement learning is the idea of tile coding. So in tile coding, imagine that you have the grid world that we also had visited a lot in the previous lectures. And what we have seen there is we had a discrete grid where we had different states just described by their cells. But now imagine that actually we have a continuous state space. So what we usually see also in something like a frozen lake environment, we can take any position on the state space, and it might also be between such discrete states. And in order to actually deal with this it's actually to use tile coding. In tile coding, the general idea is to say, okay, I have a number of 10 features, maybe, meaning that actually we define 10 tilings. And what we actually do is imagine that your tile is describes a discrete state set. In this case, we have the continuous grid world in here, and we just define a 4x4 tile, which is discrete, and we define it on different areas. So we move it. So we have one tile, and each tile is a little bit moved over the state space. And what we then say is that a point that is actually represented through a continuous position in the original 2D state space can also approximate it actually by a number of discrete occupancies in the different tilings. So in this case, from the blue tiling 1, this cell would actually be occupied through this continuous position, meaning that this results in a one hot vector. Actually, in this case, it's like 4 to 4, 16. We have a one hot vector of 64. We have a binary vector of 64, and on 4 positions within this vector, we actually see a 1, and in all the others, we actually see a 0. And this actually then defines our two-dimensional continuous state space, state point, somewhere within the overlap region of these tiles, making it essentially a discretization of the continuous point. What you also could do is actually, while this is a very naive way of actually choosing your tilings, what you could also do is induce prior knowledge to your system. So actually, if you want to have a more powerful approximation in some areas of your state space, you could also define the tiles to be of different size and also to be at different locations within your state space. So in this example, you can also come up with absolute positions of your tilings to actually represent points where you actually assume the position to be more often, where you want to have a more powerful predictive accuracy. You have a fine-grained overlap in here, and by this you can actually derive a little bit, or actually you can steer a little bit the approximative power of your feature extractors. So tile coding is something that is usually, or that has been usually used very often and very exhaustive. And what you see here is actually a continuous environment called mountain car that is actually trained with tile coding in combination with linear salsa. So actually in mountain car, the problem is that you have a small card that initially starts at the bottom of the valley, and the goal of the card is actually to go up to this point as quickly as possible. And actually it would be not a very hard problem if we would not define something like constraints. So in general, the problem is defined like this: that the power of the car is not sufficient to actually directly go from the valley to the top, because actually there's not enough power in your engine. So what you actually need to do is you have to gain inertia through wriggling around the valley to actually gain some more acceleration and to actually yield it to go to the top. The action space is defined in a two-dimensional fashion. So it's first defined over the position, which could take values between minus 1.2 until 0.6, and if you reach 0.5, actually you have finished the episode. You get a minus 1 time step. You get a minus 1 reward per time step, and if you don't manage to go to the top of the valley within 200 episodes, the episode terminates. So this actually encourages the agent to go to the top of the valley as quickly as possible in order to reduce the negative reward that it actually gets. And of course, this is a continuous state space defined over a velocity and position, and you could use the idea of tile coding to actually discretize the state space and to solve it using the methods we actually already learned, in this case linear salsa. In this case, it's actually solved using coarse coding, which is very similar to tile coding. You can just imagine that now we do not talk about tiles, we talk about circles that we put an overlay over the state space. Nothing else like tile coding with circles. And what you see in here is that we have our tiles or our circles fixed, and we just approximate the parameters W in our parameter vector in order to actually derive the correlate value function that in the end looks something like this. So yeah, exactly. One more thing to mention: there's another well-known basis function that has also often been used in linear value function approximation, also in more recent work, which is actually about radial basis functions. And the thing is, RBFs or radial basis functions, they are actually a natural generalization of the coarse coding idea to continuous valued features. So in the coarse coding idea, or the tile coding idea in general, we derive this binarized vector, which is actually very large and it has very many zeros in it. And Actually, there's much more zeros in it than ones, which is okay. It's a sparse representation, but we also lose a lot of information with that. So RBFs is actually a natural generalization of this, actually meaning that how close is actually our continuous valued feature to this radial basis function in terms of how active is our radial basis function towards this position. And radial basis functions are actually something like Gaussian bell-shaped. They have something like a Gaussian bell-shaped response defined by their feature width actually and their center state. And depending on where the actual real state is, and we put it into this feature kernel, we actually get an activation in this. So if we have a point something like here, we would have an activation of this value for C1, we have an activation of this value for C1 minus 1, and we have a close to 0 activation for the kernel C1 plus 1, CY plus 1. Also something to notice about, if you use radial basis function as in order to transform your state space into the feature space, you could also think about like moving around the centers or the width of your radial basis function to actually better approximate the things that you see in practice. This actually works if you fine-tune it in practice, so you actually can move around the centers of your radial basis function to while training, use more radial basis function in areas where you want to have more predictive power approximation of your actual state. However, this introduces a nonlinearity in your optimization function, and you really need to carefully exploit this in practice. This requires a lot of tuning to actually being robust, and the benefit is not that much that you would have expected from a first point of view. So actually don't change the centers and the width of the features, and then you can simply estimate the parameter vector W to actually learn your value function approximation. If you also do this with linear Sarsa and RBF features, you end up in the value function looking like this, which is actually very similar to what we have seen with tile coding or coarse coding. Fun fact aside, there is only this drawn image from Matt Kretschmer. There is no real image from it, so it somehow he somehow actually printed it out on a slide and then added velocity and position on top of this here because he actually forgot it actually to plot it. But there is no like digital version of this plot, so you will see this plot a lot in practice because there is no digitalized version of it. Okay, so we talked a lot about linear value function approximation, and now the question arises, why should we actually care about linear value function approximation? I mean, all of you or most of you have actually seen different lectures on where you actually have also gone beyond linear value function approximation. What you've seen is basically this is very similar to actually using SVMs with custom kernels on top of it. But you all know that actually neural networks as nonlinear function approximators are the way to go in many applications in machine learning and deep learning. And the question is, why should we use linear value function approximation? And I said it in the beginning, we always care about the convergence of our control problems. You have seen that we have this generalized policy iteration scheme, and we do the bootstrapping of our target values, and we have the off policy and on policy way of actually evaluating a policy. And the thing is that this is also making training in general prone to instabilities, and this is something that we always try to get around. And there is actually proofs that actually prove the convergence of Monte Carlo and Sarsa and Q-learning, all for the tabular representation of your state space. And you can actually also derive proofs that actually guarantee that Monte Carlo control and Sarsa in this sense are also converging in the linear function approximation case, in terms of like they are not nearly like getting to the optimum, but they're chattering around the optimum because actually approximating something. And you introduce an error through the function approximation, which actually leads to the fact that you chatter around the near optimal value function and you will always have some small error. There is actually no proof for Q-learning for the linear function approximation case because you have the off-policy idea and there's a high per sample variance, which leads to instability during training and hence a divergence of your values. There's also a nice illustrative example in David Silver's slides about value function approximation in the end, where you really come up with an example where in Q-learning, in the linear value function approximation case, your Q values really diverge and they go into minus and plus infinity actually during training. And in the nonlinear function approximation case, there is actually no convergence guarantee at all, so there's no proof that anything, anytime converges in the end. So this is actually why linear value function approximation is so nicely been used in practice. So now we talked about, can we approximate our V or state value function or state action value function with linear value function approximation. And the thing is, there is the, maybe some of you know this, there is the universal approximation theorem stating that you can actually approximate, given enough parameters, you can approximate any function. So the proof is out of the scope of this class, but however, you can approximate any V or Q value function with a linear function approximator. So the question now remains is it easy to find such a linear value function approximation? And let's maybe do some illustrative example first. The first is, I would say, yes it is. Let's now assume an example grid world problem. And in the example grid world problem, there is actually, you are somewhere in the grid world and there's no obstacles in it. You can do deterministic actions, up, down, left, or right. There's no discounting and you get a -1 reward everywhere except +10 in the goal state. So actually this is the 0, 0 point and X and Y actually go in that direction. And the question is, now, how can you actually find a linear function approximator that actually approximates the value function well? Let's start ahead and just represent S as a feature vector like this. So we just define a feature vector with 3 elements. It's just the identity and the X position and the Y position in their discrete elements, in their discrete state elements along the X and the Y axis. And then we just define our linear value function approximation, which would just be defined as a function so that our value function of S given a parameter vector W is nothing else than the transposed representation of the state of the features actually, which is 1xy times our feature vector, which is in this case 3 values, and we can just analytically calculate this, given that our state value function of S given by the parameter vector W is nothing else than V0 plus V1 times X plus W2 times Y. And yeah, so actually, how would this actually look like? How would actually a perfect parameter vector W look like if we would run such an optimization? We could just say the W vector would look like 10 minus 1 minus 1, and if we use this use this parameter vector, actually our state value would be defined in this case as the Manhattan distance to the goal, which is exactly what the value function looks like in this case. So given that parameter vector W 10 minus 1 minus 1, we actually have represented our value function through just 3 values in this, like 49 cells. We actually have only 3 parameters that we need to store given this parameter vector. However, what if the reward changes? Now look, in the previous slide, in the previous example of this, in the previous version, we had the 10 reward in here. Now we move the 10 reward towards this cell. The question is now, through a parameter vector W with 3 elements and these 3 features, can we actually come up with a good approximation of the value function? Maybe think a moment about answering this question. So actually, no way, it's not possible. So you cannot actually find an approximation that uses this state features to actually linearly estimate the value function. What you then would need to do is just define another feature with which we can actually derive a linear combination of that. So what we in this case would do, we would just define an additional feature z, and an addition, which actually then also requires an additional parameter w. And the question is, could you come up with an additional parameter or feature z that actually helps you to linearly derive the value function? And indeed, yes, you can. So you actually just define a z to be the origin of, or like deriving the actual state of the actual settle point of your value function. And if you derive c with this formula through the original state space, you actually can define a linear value function, a set of parameters w that actually approximate your value function. So the thing is, maybe come back to the question, is it easy to find such a linear function approximation? In fact, it is not. So actually, while the problem of estimating the parameters w to actually do a linear combination with the given features, this is actually giving a lot of pressure to defining a valuable state set of features that actually allows a linear combination of them to estimate your value function. And this can be also very problematic, and there is a lot of work that actually considers deriving a set of linear features to do reinforcement learning through state action value function approximation. You see this a lot before around 2012, where this was the majority of things that dealt with this problem. So if you want to do Tetris, we also had Tetris in the beginning of this lecture. You could define a feature set that's using the landing height, so basically the height of the last piece that has been added, eroded piece cells, row transitions, and so on. So it's a list of different features, and what they actually did is they actually derived these features from the input image, and with this set of features they are actually managing to derive a set of parameters, and with the linear combinations with the parameters and the features, they actually can do value function approximation. With Pac-Man, it also has been managed to do this in the past. We also had a few ideas of this I also had in the previous video, where you define features like is there nearby walls, the distance of nearest targets, nearest by ghosts, is it trapped? Is Pac-Man trapped or not? Things like this, and if you define features like this, you can also come up with linear function approximators that actually solve the problem. Besides games, there also have been control problems that have been used with linear value function approximation. What you see here is actually card pole. We also had card pole in the first slide, and I also had it as a running example in this video, where it is actually defined by, the state space is actually defined by the position of the card, the angle of the pole on the card, the angular velocity of the pole, and the velocity of the card. And actually, what you see here is a number of well-tuned radial basis functions. In this case, it's 9 radial basis functions that are defined over a 3x3 grid over the 2-dimensional state space that has been used actually for control. And you can actually then come up with this state representation and then do LSPI, which is in this case least squares policy iteration, where you can actually solve the problem in the continuous state space using this feature feature set. The same with control problems of bicycle balancing, so this is the bicycle balancing and riding problem, where you actually need to follow a trajectory and you actually have to balance the bicycle at the same time. And you see that also in here you can come up, if you like really well tune your feature space, you can also really like come up, in this case it has been 20 basis functions. You can come up with a number of basis functions that you can actually use to approximate your value function through a linear combination of them. But what you also see here is that coming up with a number of linear basis functions is not like a naive thing to do. On the one side, you want not to have too many of these basis functions because you actually find parameters that describe their combinations. And you also need them to be actually complete to define your Markov state well and to define your control problem well, to actually know that you can actually solve this with this representation. Okay, so we have seen that we can approximate actually any state value or state action value function with a linear value function approximation, and it is not very easy to find such linear function approximators, namely the features that we actually need to derive from the state space, because they need to be complete and not to be too much. And the question is now, having seen the idea of, or the revolution of neural networks and their predictive power and extraction of features from raw input, the question arises, why don't we replace the linear approximation that we use and actually do a nonlinear approximation with neural networks? And the thing is that, as we have seen before, that theory tells us that this probably doesn't work. And the thing is, we cannot derive any convergence guarantees, and reinforcement learning is always an area where we really care about stability during training, and nonlinear function approximation are really difficult and hard to stabilize during training. However, also in the very past, there are some applications that actually did it. So there are applications that use neural networks to actually approximate a value function. And the very first example of this was actually TD Gammon. TD Gammon was actually evolved to the world's best backgammon player, and it uses a neural network with only 80 hidden units, and it used reinforcement learning for 300,000 games of self-play, and in the end was one of the top players in the world. And this early idea also used neural networks to actually encode the value function. And I mean, we will not go into the idea of TD learning anymore, but we actually define an update rule to our network weights actually, which is like a TD lambda step over the parameters and the value function, and we will like take a step with respect to the gradient of our parameters in order to optimize the values of the hidden units. And this actually works out pretty well in practice. So with you see this. So this is with 10. This is this is actually the performance of the agent. It's not the predictive power of the function approximator. It's really the performance. And what you see is that with an increasing number of hidden units, you actually approximate the value function more accurately, leading to that you actually can use the value function estimate of your neural network to do greedy policy improvement and actually to do control within a backgammon, within playing backgammon. So this was one of the very early results and successes where you actually see something like the idea of deep learning and the idea of neural networks within the control problem of reinforcement learning. And based on this idea, which is like today it's almost 30 years old, based on this idea, we actually derive a lot more of that and more powerful techniques when we talk about deep Q networks in the upcoming video.